Now that we know how reactions occur and in what ratios, and we can use those molar ratios to perform stoichiometry to estimate the quantity of reactant that we need and potentially product that we get. Now we need to figure out, okay, how long is it going to take me? Right? Because it's all fine and dandy. If you look at an industry, wholesale buyer customer and are like, hey man, I can give you 57 tons of Advil. Sick. Okay. Cool. Right? The wholesale buyer customer will say, great, I need it by March. And you're like, oh, okay, well, right? Maybe not by then. So what we're going to talk about is, again, another important feature of making chemistry monetarily useful in our economy, right? Is figuring out how fast it goes. Also, a little quieter, TA, sorry. Also, figuring out if we should be concerned about a reaction that we don't want to happen very fast, like a side reaction. How could we slow it down? And the end goal is, like in chemistry, a lot of it is called manipulation. How can I identify the patterns of molecules and know it so well that I can now control it? Okay, so that's kind of what we're getting at, and this is going to be our study in kinetics. So chemical kinetics is the study of the rate. Okay, study of rates at which a reaction occurs. And the factors that affect it. And I do not know if it's E or A effect, but I'm not an English teacher, so I'm not worried about that right now. Okay, different reactions have different rate of reactions, okay? Which, conceptually kind of makes sense, right? Kind of like how when you bake, different things take different amount of time to cook, right? Even if you use the same ingredients, even, right? So primary method of measurement is tracking the change. Track the change in concentrations of your reactant species over time, giving us average reaction rate, change in concentration for a given species over time. Okay, and that would be molarities per second, right? Throughout the reaction, it's important to note why it's valuable to take average, because as you progress in a reaction, you just simply have less reactants to react. So one reason why we love average is that naturally the reaction will slow just as it run out of reaction. So if we were to take the reaction rate at the end, it would be far misconstrued because you're simply working in a non-favorable environment of just not having enough present. So what we say is with reaction progression, the reaction naturally slows over time. So average gives us more accurate, okay, description of all reactants present in an ample amount. How fast can it go? Yes.
Why don't we measure reaction rate relative to the amount of stuff you have rather than the rate itself?
I don't think I understood that question.
As in, if you have more stuff to react and that makes it react faster, why not measure things relative to the amount you have?
Well, we're going to hit that to integrated. Yeah, like a derived way of doing it. Okay, so let's just talk about some general laboratory methods for this preliminary understanding. And by the way, this whole lecture today is just the introduction to get you to the AP level. This is just the background, okay? So one, you can measure the concentration of each reagent or reactant species involved directly. Like, right? So one way is actually titration, right? We can use titration to determine the molarity of a species. You could use gas production wise, you can measure the pressure. Pressure is a indicator of how much concentration of a gas is present. Okay, we treat it almost equivalently to saying molarities of gas. Instead, we say pressure. FYI, when you do these measurements for gas, just keep in mind it has to be a closed container. Sounds obvious. You'd be surprised how many sad moments happen in lab when it comes to gas and flaky powder. I remember being in lab after a 4-hour synthesis, and my lab partner, oh my God, I still remember him, Layal. If you ever see this, I still have a grudge against you. Layal, it was hot in the lab rooms. He turned the fan toward us, and all of our beautiful crystalline powder of ibuprofen that took 4 hours, 2 rounds of lab, blew away. I could have killed him. Yes.
What's the word after involved?
What do you mean involved? I don't see involved.
Directly? Okay.
Oh, involved directly. Okay. So anyway, then you can do non-direct measurements, which is what we had to do as we swept up our product off the floor, which was now super contaminated. Okay. Non-direct measurements include measuring a correlating property. So a property that can indicate when concentration change has occurred. So that can include several things, right? That can include volume, okay, pH for acidity and basicity, presence of a certain amount of ion, right? That is stoichiometrically related to the compound it's carried with, right? It could be mass, and it could be, in here we also say pressure is like also, it could be considered direct or indirect, right? How, depending on how you look at it. So the third way is that when you're in solution, we can measure the color change, which is directly digging deeper into the idea of titration and pH. So, of course, I'm going to mention titration again. Okay. But also, when we talk about pH, I mentioned earlier electrodes, right? That's a really precise instrument that we can use for measuring pH and therefore ion concentration. And I think I was saying much greater accuracy and precision than like the slips or your eyesight, right? Your eyes doth lie to you. They do. What happens is when we do it this way, okay, titration with pH electrodes, what you can do is you can create a graph. And from that graph, you can extrapolate a relationship. Extrapolate. Okay. And so what we often do is we often will partner this also with color spectrophotometry. Because if we have a certain degree of colorful solution, that indicates to us a certain degree of concentration, which can then be used in Beer's law with the instrument spectrophotometry. Or sorry, with the method of spectrophotometry and the instrument called a spectrophotometer. Okay, and dare I say Beer's law. I've taught you Beer's law very briefly. But here we are, nonetheless, right? So when it comes to the math of it, it's not too crazy, which is kind of nice. So it's averages, and you guys should be quite familiar with averages. So what we say is that the average reaction rate involves derived units. And if you have a derived unit, you have the potential to now do dimensional analysis okay. And therefore, if you have that ability, you also can partner it with stoichiometry and molar ratios. And of course, that means that you now can, okay, predict amount or change in amount of a given species. So the big idea about why these are useful to us and that we're going to refine tomorrow and the day after in a much more advanced way is that we are now able, okay, to quantify that the rate of change of a reactant slash product concentration can now be determined or described, right? Term and described by stoichiometric relationships and that's like the real value, is that the rate of change of reactant and product concentration can be determined by stoichiometric relationships. And of course, the big helpful thing is that if it's a rate of change, you're doing it within a time limit, and time is valuable. Time is probably your biggest value, right? Your biggest scarcity and the biggest value when creating a certain monetary of saleable amount of product, right? So here we have a practice problem where you're given a series of data.
The word after product, say
Concentration. So here you're given a series of information, and I'm going to walk you through each portion for this problem, and then you will have a practice problem to do on your own afterwards. So here we have paraffin candle C2858. That's a hydrocarbon, FYI. Don't forget your hydrocarbons. That's a CH only molecule, a hydrocarbon. And we place it in a petri dish, we put it on electrical balance, and we combust it, okay, for 15 minutes. The accompanying data is collected. A, calculate the average rate of combustion of the paraffin over the entire 15 minutes. So first and foremost, okay, if you're given data, you're going to be asked to use it. Okay, so if you're given a data table on the AP question, don't stray very far from the data table. It's the information they want you to pull is on there. Okay, so what we look at is, as far as over the 15 minutes, A, right, find your average. So what is the change in concentration over the 15-minute time frame, right? Easy peasy, lemon squeezy. I start, all right, at 180 and I end at 170.01. So I'm gonna, this is not too bad at all, you guys. One's absolute value of 170.01 minus 180.00. This is nice sig figs, guys. Look at these 5 sig fig values all over 15. Okay, giving me a rate of, I'm combusting it, which means I'm losing it. So I'm going to say 0.666. That's a really unfortunate number. Grams per minute consumed, used up, or combusted. Okay. So make sure you're also pairing the conceptual with the number. Okay. Is it me producing it, or is it me using it up? Okay. B, calculate the average rate of formation of the water vapor for the same period. So now we're looking at a product. So what you're really going to look at now is, before you can even answer that question, is you're going to have to write the balanced chemical equation. So your balanced chemical equation for combustion is your hydrocarbon, C28H58. And I'm just going to give you the balanced reaction. I assume you can do it on your own, but just to save us some time, 8D5 oxygens goes to 56 carbon dioxide and 58 water molecules. Okay, so now we have to relate our paraffin to our H2O production. So it goes 2, 85, 56, 58 as the coefficients. 2, 85, 56, 58. Yes.
So in regards to sig figs in the table, before 3.0 and 15.0, for example, isn't that changing sig figs from C to sig fig?
Yeah, that's a great question that I don't know why they did it like that. Okay. So, Maggie. So, what we do now is we know a rate of consumption of the paraffin. If we can convert that to moles per minute and get into moles, then we can stoichiometrically predict the moles produced of water and then convert to grams. So we start with 0.666 grams per minute of C28H58 paraffin. We know that for every mole of C28H58, we have 394.0 grams of C28H58. We also know that for every 58 H2O produced, we consume 2 C28H58. And we know that for every mole of H2O, we have 18.02 grams of H2O. And that gives us a final value as for the rate of production per minute for water to be 0.882 grams per minute for produced of water vapor. So we're seeing average rate, this derived unit being now used in a stoichiometric dimensional analysis quantitative process. Math. Okay, B. We just did that. C, note the mass loss in each 3-minute time increment. Comment on the rate of combustion of the candle during the entire trial. Suggest a reason why the rate of this reaction isn't greatest at the beginning with a steady decrease as time passes. Talk with a neighbor about that. Just don't have to write it out. Just talk with a neighbor. Yeah, because over time you just have less paraffin. I mean, I'm assuming your oxygen is in excess, okay? But you just don't have as much. So naturally, as the reaction progresses without a continual resupply, you're going to get a slower rate of production, which is going to be reflected in an instantaneous, okay, slower rate of reaction, which is why we like the average. Alok.
Isn't it really decreased significantly though?
Yeah.
I feel like
Yeah.
the question was asking is like why isn't it?
Yes, just a reason why the rate of the reaction isn't greatest at the beginning.
With a steady decrease as time passes.
Why it isn't with the steady decrease in time passes?
Oh, I didn't misread that whole question.
Yes.
Oh, that's exciting. Man, I shouldn't have clicked record yet. Sorry, guys. Notice the mass of the combustion.
Why is
I
it
mean,
in
it's,
this case
it's
what
a,
they want
it's a
you to notice is
cylindrical
that it
candle,
is
so you can only
constant.
burn so much.
It is
paraffin.
constant.
Yes.
That's annoying.
Yeah.
The amount
Fix
of
it.
reactant you have only really matters when you have either a reaction in solution or in gas. If it's just solid burning, like there's one combustion site at the top of the candle, it doesn't matter how big the rest is.
So I guess also they might be getting at is because of your stoichiometry. It will stay consistent in how it reacts stoichiometrically. I don't like that C question. And you know what I realized? I don't think we answered it because I didn't like it last year. Yeah, I don't think I like that. Make a note to self. That's a crappy question because it defies what we were talking about earlier. So that's a crappy question. Let's move on. Okay. Try sample problem. The next one on the next page. Oakley dokley artichokes. Hopefully you got this outline of dimensional analysis process. You were given a certain amount of time. You know that your rate is in moles per minute, so you want to convert your time to minutes. You then use your derived unit average rate to estimate the amount of moles of sucrose consumed. Then you use your molar ratio, your stoichiometry, to predict, given that amount of consumption, how much can I produce of carbon? Then you convert the moles of carbon produced to grams. And what was the final value?
59.5 grams.
59.5 grams of carbon produced in 30 seconds.
I used a completely like different equation.
What?
Like, oh,
Did you just reorder it?
no, it's just like different. I think you just like you did the full thing with all the units and stuff, and I just.
That's fine. On the AP FRQ, there are certain problems where they give you a point for part of your conversion dimensional analysis. particularly moles to moles conversion. They like to see you identify moles to moles between two substances.
I have no idea how to write it out like that. Like I could probably. It's like.
Isn't that how I taught you in the beginning though?
Yeah. Yeah, it just makes more sense to me to like write out the numbers though. Instead of, like,
Okay. Thank you. Thank you. I will keep that in mind when I reflect on my value as a teacher. Thank you. Okay, so let's talk about some factors that affect rate of reaction. So reactions are all about particle collision. So surface area, it's one way that we can increase the rate of reaction. So particularly when we have reactions are heterogeneous. Okay, when they're heterogeneous, that means like a solid with a liquid, or yeah, that's like particularly the best example, a solid with a liquid. Okay. We see that if you increase, all right, surface area, you will increase the rate of the reaction. You just got more space. It's like kind of being in a room that's really tight, full of people. You're not really, if you're sardined, has anyone played the game Sardines? No, yes, couple. Yeah. Childhood? Did you guys not have like sleepovers and birthday parties where you play night games and you try to like terrify each other? Okay. Some methods that we do is you can crush your solid substance. When you crush your solid substance, you make it into a powder. When you make it into a powder, you have smaller breakdown of the particles, which allows, or a big sample of a part, certain type of substance, which allows you to have more contact. You're not being blockaded, right? Think about getting to a block of salt, trying to get to all the salt particles inside the block versus crushing the block to get to the particles in the middle, right? The one exception of this, okay, is gas phase. This does not work. For the gas phase, this does not help you. And then certain liquids, this does not help you. So certain liquids, for example, super viscous liquids, they're not going to spread no matter what if you increase surface area. Like they're just not going to spread. Certain liquids. So it might not be the best way to increase rate of reaction. Another way to increase, very viscous, like thick, like ketchup. Think like goopity goop, like your snot. Yeah.
In the case of liquids, what exactly does surface area have?
It's heterogeneous. It's solid with a liquid. It's a reaction that includes both. Yeah. Amount of sample is also, right? Simply having more particles. All right. So if you increase your amount or your concentration, you can increase the rate. Okay. This, generally speaking, is true across all states of matter. Gas pressure wise, you can increase the pressure. You can increase the rate of reaction. And here's why I emphasize the word gas. Pressure does not help you with anything else. It only helps you with gases because gases have to collide. If you do not force them into a setting where they physically have to come in contact with one another, you're going to have a super slow reaction. But simply squishing more solids together doesn't actually help. It's the level of exposure that those solids have that help. So exceptions are basically solids and liquids. This does not work. Right? Now, a guaranteed, really effective way that most chemists go about increasing the rate of reaction, Maggie, why? Most chemists put the phone away, girl. You were gone a day. You do not have the opportunity to sacrifice. Okay. Is temperature. Temperature is like a fail safe way to increase rate of reaction, and it's super easy to make that happen. It doesn't take any extra work. It just takes cranking up the setting. Okay. And here's why. Because, and it's actually the most significant factor. Okay. It's like hands down the best way, easiest way to produce guaranteed results, right? Increase temp, increase rate. Here's why. This is where the Maxwell-Boltzmann distribution comes back into play. When we look at the average kinetic energy of our molecules, this shaded area actually is quite significant because it represents the percentage of particles in a sample that are moving at an energy large enough to collide with enough force to actually bring about breaking old bonds to create new bonds in forming a new molecule, right? Because you have to break apart your old reactant species to form your new reactant species with their new bond arrangement. You can kind of think of it like a high five, okay? No matter, okay, a good high five, you know that clap sound? Or I was just at the tennis game. There's like that special like pong sound when it hits in the right position, but also with the right force. There's a special, we know this in a lot of areas of life, a designation of force and speed that produces the results that we want. The same is true for particle collision and reaction completion. So by affecting temperature, you basically raise up, you increase the percentage of your particles to maybe include up to here now. Now you have this many more particles that can get to that energy necessary to actually collide with an effective result. All right. So the Maxwell-Boltzmann is really helpful in showing us the percent of particles that have sufficient energy. I realize that does not look like a word, and I will fix it. Sufficient energy to react successfully. Okay. And I realize significant does not look like a word. I will also fix it. Oh, I put the dot. There you go. Now, there is one situation where temperature does not work. Can anyone tell me what state of matter that this would not help us with? Gas. Because think about it. If the whole idea is that your reaction collides more and you increase the temperature for a gas reaction, where do all those gas particles go?
Away from each other.
Away. Okay. Now, this would obviously be assuming somewhat open container. It might be okay if you increase pressure too, so they're colliding as they get into tighter areas. But generally speaking, we don't confidently use temperature to increase the rate of reaction for a purely gas system. Okay. But it could be argued, it could be effective if you had some other parameters around to make sure. Showing us the percent of particles that have sufficient energy to react successfully.
Can I ask a stupid question?
No, it's okay.
Why exactly do particles react in the first place?
Well, particles are always moving, so they're always colliding. And that collision is bound to produce some effect. But there's also attractiveness that occurs between the particles. We call it reactivity series, or predicting that particles are always on the hunt to become more stable. So if another particle comes along, sometimes it's more favorable to break this bond to form a new bond with the other one. Right? The affairs of chemistry, single displacement. Otherwise, it's really just kind of based off exposure to collision. Like, it's just like they collide. And oftentimes in our world, we have just manufactured the settings where we want specific things to collide. But the origin of the universe was basically a hodgepodge of collision timed perfectly with the cooling of the earth to produce the necessary slower motion needed to conserve certain atom production and increase other. or even get rid of. There are some particles that were created that no longer exist, but that were there for like a nanosecond. Yeah. It's really cool.
Each other and some of the bonds are broken and new, more favorable bonds form instead.
Yeah. And if you actually want to read a really amazing book, this is actually what had me start being interested in chem when I was in high school. It's called Atoms by Lawrence Krauss, Krauss. It talks about the story and formation of an oxygen atom 9 nanoseconds after the Big Bang and how it's formed and how it goes and then till the ends of the earth. And I actually have a TED Talk presentation that I did on it that I still have. It was the moment I fell somewhat in love with chemistry, and it wasn't until sophomore year of college that I actually decided to become a chem major. But that was like for my class, that was the assignment because I did an independent study. I was already done with all my sciences by the time I was a senior. So I did an internship and an independent study. So, but yeah, it was a really cool book. I still have very fond memories of that book, and I could give you my presentation, and I loved it. It was amazing. It was so cool. So, all right, the fourth factor that kind of is a given in terms of affecting the rate of a reaction is the nature of the reactant themselves, right? So the chemical behavior of the reactants, okay, are going slash particles are definitely going to play a role in how fast your reaction reacts. So obviously, more reactive species are going to have a faster rate. So like if you get fluorine involved, Sophie, you good? You good? I know, I feel you. I feel that way in church. I go, fluorine involved, okay? It's going to probably be, unless bound very well to something that stabilizes it, highly reactive. It's gonna be hipping and popping, okay? Also complexity of the substance. If you're trying to merge a very complex substance and break it down with another substance, and you're trying to break sufficiently those bonds, you would expect that with increased complexity, larger molecule, more variance amount of atoms involved in that molecule, your rate of reaction would actually decrease because it becomes incredibly important to, one, smash that thing hard enough that it actually breaks apart, and then two, like collide in the right places. If you're trying to break certain bonds and you have a series of different complex atoms involved in the molecule, it becomes paramount that you collide in the right positioning. Okay. And so that's why it becomes slower because it's just harder. Okay. Also, of course, state of reactant in general. We would assume that for the most part, generally speaking, gas reactions are generally likely to react at a slightly faster rate than purely liquid reactants or purely solid at room temperature in aqueous solution. Yes.
Like higher complexity, the reaction goes down. Does that mean that there could be like multiple reactions?
Yes, that's where we get side products in chemistry. So a lot of times one reason why we get like 33% yield is we made 60% of something else that we did not want. And it's really hard to control those collisions. So
Getting a mental picture of some guy taking a piece of plant and throwing it and
wow, I saw this really cool Instagram of these guys in like hazmat suits, like lighting, like he had like a shovel of, I don't even know what type of powder, and they lit it and they hit it and the sparks went everywhere. And I was like, that was such a cool experiment. I wish I did that. Okay, so catalysts are another factor that can affect rate of reaction. And we're going to delve into catalysts further because it's going to become particularly important and when we talk about reaction mechanisms in the coming days. Well, I'm going to do a little intro to it now. Catalysts are external, so non-essential to the reaction. They are not actually involved in the reaction. External chemical species. Okay. Chemical species. Okay. Added to the reaction to speed up the rate. Okay. But is not reacted itself. So it would never be part of the chemical equation. Like sometimes we put it above the arrow just to acknowledge that we used it, but it's not an essential part of who's actually having their bonds broken, who's actually having their bonds formed. A catalyst would not be involved in that. A couple bits of terminology is that you want to know is that we say that the catalysts regenerate themselves. They are regenerated. So that means they are not consumed. And when you add a catalyst in the beginning, you should find that your catalyst is present at the end too, because again, it is not actually involved in the reaction. Are you okay? A lot of information. It's a lot of information. You okay?
Oh, yeah, I'll watch the
Okay. Yeah.
What exactly is the catalyst do?
Sometimes the catalysts, well, in biology, your catalysts are your enzymes. They sometimes hold down and trap the necessary parties and position them in the right way. Sometimes your catalysts create an intermediate molecule that makes it more favorable for your other particle to come along and collide with it, or more attractive to it. So sometimes your catalyst does create a pseudo reaction within the reaction, but is then regenerated at the end because it is eventually kicked out. It is not absolutely necessary. It just makes it better. It's kind of like, have you guys ever heard of a meet cute? Okay, when a friend introduces you to someone else that maybe you could have met naturally, but instead they speed up the process. They invite you out to like a group dinner. Okay, that's one way a catalyst can work. Another way a catalyst can work is your friend holding you down and saying, hey, talk to this person, right? Holding you down like a biological enzyme. And there's like one kind of other way, but yes.
So like if I were to pass hydrogen over a catalyst of tritium, what is the tritium catalyst actually doing in order to like react with it?
Bro, I'd have to look at that. I don't know every single like reaction out there.
Energy?
Well, it's making it energetically more favorable to have that interaction occur. So it actually is lowering the overall energy. Yes. Okay. Wes.
How is it lowering like activation?
Because what it does is it creates a new pathway, and that's when I'm going to get into reaction mechanisms. And I will explain it better with an illustration. But that's not today, that's tomorrow, or maybe 2 days from now. Any other questions? Okay, so just so you know, I mentioned this earlier, we do not put the catalyst in the reactant to products, but sometimes we might put the catalyst above, just so somebody knows the way that we made this reaction is we sped it up. Because oftentimes we track the rate of how long it takes to make a compound. Because if you're a chemist and you're trying to reproduce a reaction, you kind of want to know if you can leave it overnight or if you have to stay there for 5 hours. Right? There are some reactions that decompose after a certain amount of time, and you have to catch it before it starts to decompose. There's some reactions that you can leave running for 48 hours. There's some reactions that you have to leave running for 48 hours. My reactions were ran over an 8 to 12 hour period. So I could go home, get dinner, go to bed, but I have to come early in the morning to catch, and I'd have to extrapolate, purify twice, and then analyze. Okay. Biological connection, that would be your enzymes, baby. Your biochemical catalysts are your enzymes. Okay. And I don't know why I put a comma. That was unnecessary. I should have put it like a enzymes. Okay, so for this practice problem, I'm going to let you guys address this, and then we'll quickly talk about it, and that will be the end of class. So just take about 2 minutes to try to figure out methods. Take note of the state of matter, okay? And then we'll talk about it. So for the first reaction, you guys should have noticed this was a heterogeneous mixture, okay? You could kind of get into the details of surface area, but a surface area really does work best with solid and liquid mixture. It really does. So what's one way that you could increase it? That's like a fail safe. No, because what happens to the gas? Add a catalyst. Like, again, maybe if you added increased pressure, right? You'd have to kind of do a twofold thing. Add a catalyst is hands down for both. Like straight up adding a catalyst is like hands down good way to do it. What else can you do for A though? Just add more. Like literally add more. Done. You just had to list 2 ways. What about B? Temp. Stir. create more kinetic energy, create increased collision. Like literally there are so many. You could have said add more. The second one tends to be a little bit more versatile in options. And that's it, guys. So you only have like a 10-minute, if that, walkthrough. And it's not even AP problem walkthrough, but I would take a moment to try some redox problems while you're here in class for the last 10 minutes of class for the quiz tomorrow. All right, guys, good luck.